We're going to finish with another messy one here. There's a little bit of a tricky idea in play, but what we have here when we look at x going to infinity, this what we have is a 1 to the infinity indeterminate form. 3 over x, as x gets very large, goes to 0, so we have a base of 1 and an exponent of infinity. So we have this base getting closer and closer to 1, being raised to a higher and higher power. That's the conflict involved here. Now, L'Hopital's rule doesn't do us any good for a 1 to infinity. Remember, we need, as always, a 0 over 0 or an infinity over infinity indeterminate form. What we're going to see here is going to work for 1 to the infinities, 0 to the 0 indeterminate forms, and infinity to the 0 indeterminate forms. Okay, the technique that I'll show you right now. So what we're going to do first is we're going to let L equal this limit that we have. So L is the limit of 1 plus 3 over x to the x. And remember, L is what we want. We want to find the value of L. So the problem, of course, is we need this 0 over 0, infinity over infinity, instead of something with an exponent. So how do you get rid of an exponent? Logarithms, right? Logarithms get rid of exponents. We're going to take the natural log of both sides here. And the reason we do that is that our log rules are helpful in getting exponents out of there. This is x times the natural log of 1 plus 3 over x. We used our log rule. This is the log of all of that. I guess we close that up and make it more clear. So that x comes down outside of the log, and we no longer have an exponent. And that's great, but what do we have? We have a limit as x goes to infinity, so we have a limit that looks like an infinity times the natural log of 1. 3 over x goes to 0 as x goes to infinity, so natural log of 1 is 0. We have a 0 times infinity indeterminate form, which we already know how to deal with now. So we're going to deal with this in the way that we've learned. 0 times infinity indeterminate form, we're going to have a natural log of 1 plus 3 over x over 1 over x. So remember, we write that x as 1 over x. Now what we have is a 0 over 0 indeterminate form, and we can go ahead and use L'Hopital's rule at this point. So that's great. We get to use L'Hopital's rule. L'Hopital's rule tells us that the limit we have is the same as the limit of the derivative of the numerator. So how do we take the derivative of this? It's going to be a chain rule. So the derivative of this is going to look like 1 over 1 plus 3 over x times the derivative of 3 over x, times the derivative of 1 plus 3 over x, which is negative 3 over x squared, divided by the derivative of 1 over x, which is minus 1 over x squared. So we took the derivative of the numerator and the derivative of the denominator separately, and you can see we've got a bit of a mess, and we're going to try to clean that up algebraically. So this is not L'Hopital's rule for this equal sign. This is just doing the algebra. So we have here a minus 1 over x squared over a minus 1 over x squared. That's going to cancel and leave us with a 3. So that's nice, that cancellation there. And so we have a 3 over 1 plus 3 over x after canceling the parts that cancel. Right? And that's great, because now we can plug in x equals infinity, or we can actually look at the limit as x goes to infinity. 3 over x is going to get smaller and smaller and go to 0. This limit is going to be 3. So that's great. We have a limit. We're not quite done. Remember, what we found was the natural log of L. What we wanted to find was L. So we have to go back and finish the job. We have the natural log of our limit is equal to 3. Exponentiate both sides and get L equals e to the 3. And that is the actual limit. That's what we're looking for, e to the 3. So this is how we will deal with any of these indeterminate forms that have exponents. We'll deal with it by taking natural logs to get rid of the exponent, and then we often have an infinity times 0 indeterminate form, and we know how to deal with those. And at the end, remember, we found a natural log of our answer, so we have to exponentiate to get our actual value.